Welcome to my talk about SwapCT, a swap confidential transaction system. This is joint work with Lukas Müller, Andreas Peter, Frank Kargl and Christoph Bösch. So let's have a look at private and confidential token transfers. Let's assume that we have a setting with 4 participants where Ponytail transfers $3 to Megan, transfers $3 to Cuball, and then transfers $3 to Whitehead. For our consideration, we look at the privacy from the view of Megan. So first we need send anonymity, so Megan should not figure out who sent her the $3. And in the same direction, we need receiver anonymity, so that you need to know your immediate recipient, but of course what they do with their tokens should be totally irrelevant to you. Then you need value confidentiality and type confidentiality for all transactions which are where you're not involved in. To deploy this whole system in some permissionless setting, we also want a transparent setup so that we don't need someone to perform a trusted ceremony. And in the same spirit of openness and privacy, we also want non-interactive transactions. So this is important, one, for functionality, that if your recipient is not present, you should still be able to transfer them tokens. And the other thing is that if you have to interact with your recipient, they might come back and stab you. So thereby it also helps the privacy if you don't need to interact with the recipients. So far for transactions, so we know how Megan can transfer $3 to Cuball, but how about swaps? So a swap is more or less an exchange of tokens in some times for another amount of tokens in a different type. And we want them to be non-interactive. So for example, Cuball wants to exchange his $3 for €1. And he just doesn't care who will actually fulfill the exchange, but of course somebody needs to exchange. Cuball cannot exchange with the system itself. But it should be non-interactive. So Cuball sends out the offer, and then at one later point, he might receive €1. So somebody might pick up the offer and then fulfill the swap transaction. So it is important that this is an atomic swap, which means that neither party can abort with a benefit or in the middle of the project and the honest party would lose tokens in this system. So that's why we need atomic swaps. And what we require on top to make the system more trading friendly is that these swap transactions should be indistinguishable from normal transaction of like non-swaps. And this helps the anonymity of this deciphering between a swap and a standard transaction. They all share one anonymity set. So why do we need to exchange tokens and work with tokens and have this notion of tokens? Because why wouldn't be just one currency with one value be sufficient? Because we saw that people use them. If we look at the Ethereum ecosystem, we have several tokens living on there as ERC20 smart contracts, and there are many of them. So between each of them, there is another one, and that continues. So there are plenty of use cases, even if only a fraction of them are useful use cases. There is definitely an interest in privacy preserving tokens. So if we look at recent work, we want to evaluate that with different properties. So we need, as explained before, we need sender and receiver anonymity, we want value confidentiality, we want type confidentiality, we want a transparent setup, non-interactive transactions, and atomic swaps within which are only make sense if we have type confidentiality. And then we just show how they achieve it with some high-level building blocks. One of the most prominent privacy-preserving transaction system is Zcash, which achieves everything except of the transparent setup. Then we have Stellar, which defines that any transaction which is representable as a rank 1 constraint system can be performed, and thereby and it works on committed values, so even type and value confidentiality is achieved. However, they don't have any notion of sender or receiver anonymity. Mimblewimble is awesome. It's super scalable, efficient. It has no accounts and thereby achieves kind of sender and receiver anonymity. The problem there is that we have interactive transactions, so you need to talk to the recipient, and then you can do a lot more fancy stuff. Quiz is a different approach, which focuses on the fact that the state growth, and in most other transaction systems, which because you cannot prune, and Quiz is able to prune stuff, but there the issue is integrating type confidentiality. So that was not suitable as a base to achieve our goal. Then we look at Monero, which uses ring-based signatures to create an anonymity set, but Monero doesn't have a notion of type, and because they don't have types, they don't need atomic swaps. And OmniRing is more or less Monero in the functionality, but with a solid formalization and a way more efficient bulletproof than the ring signatures of Monero. And we use parts of all of the different signature types or transaction systems and build SwapCT, which uses some formalization of the OmniRing, because we are also in the ring anonymity setting, and we provide an additional feature which is anonymously aggregatable signatures for these atomic swaps. So one option which we briefly looked at but discarded then is that you can also do privacy preserving exchange between chains which don't have any notion of type. So let's assume you have two Monero chains, one for dollars, one for euros. Then you can do private exchanges between them, but the metadata alone leaks the frequency of transactions within each system or within each token. And the other problem is that deploying a new token is prohibitively expensive. So let's look at SwapCT. The basic features is that it's a UTXO system, which means that each transaction consumes input and produces outputs, and inputs are references to previous outputs, and once an output is referenced, it's no longer spendable. We achieve sender and receiver anonymity by breaking the direct link to which input is used, and we have confidential amounts and confidential types due to the nice confidential commitment scheme. So how to build these atomic swap transactions? Let's assume that QWall has $3 and wants €1 in return. So QWall can sign an offer which says, I would authorize to spend my $3 node if somebody returns a €1 node to me instead. And Megan, for example, can conversely do the opposite thing and sign it. It says that I authorize to spend my €1 input if I get $3 back. And then somebody can join both together and get a more or less balanced transaction, which is then should be indistinguishable to a transaction which is probably created by QWall himself and signed. So we need to do this anonymously so that all the sender and recipient anonymity is achieved, and for offers it doesn't really make sense to hide, because then you don't know what you exchange. So there only the accounts are hidden but not the type and value. But in a final transaction they're completely hidden. So you only need to trust your exchange to scrub the values off, but the exchange cannot steal anything, for example. So our main work is how does these aggregatable signatures work like. And to start this, we assume unlinkable key pairs to the inputs. So each input has a public key and somebody has the private key to it. So QWall has a $3 input and Megan has a €1 input. And they both have the respective secret key for that. They have their message they want to achieve. So Kargl wants €1, Megan wants the $3. And they need to create a signature for the set of both signed with both secret keys. And in the interactive setting, that's super easy. They just exchange the message to the other party, then they both have the full set. They sign it with whatever signature scheme they want, and they just concatenate the two signatures, and that's fine. The non-interactive setting is way more complicated, because if we just concatenate the signatures, the mapping between who signed for which message in the set is apparent, and that hurts the anonymity. So the anonymity dictates that it has to be a true multi-signature over a set of messages. And this is not achievable by signing their respective messages, but what they need to do is they need a signature which says that for any set of messages which is a superset of my message, I'm willing to spend my input. And then if we concatenate them together, we achieve the thing. So the privacy of that is that the mapping between who signed something and which output message they wanted is hidden, and also the total number of users is hidden. And this works by, so the privacy game for that, the formal one is that the challenger distributes message and key pairs to individuals and then challenges them to differentiate how the signature was created. So how is this useful to build a swap transaction or an atomic swap transaction is that we have again this, so Kargl decides that there is a previously received $3 input and a €1 output, and Kargl signs it with the anonymously aggregatable signature scheme, which says that for all messages, so all other outputs which are part of the final transaction, as long as my €1 output is in it, I'm happy to spend my $3. Then Megan does the same as the inverse. We don't need a perfect fit here because, for example, an exchange can add a third pair to fix some small issues or pay fees or whatever. So this is arbitrarily extendable. And once they combine them together, they get a balanced transaction. And this balanced transaction then can aggregate the two signatures together, which then has a valid spending signatures for both inputs if the set is the superset of both of them. So how to build such a signature scheme? So the intuition is that we have a set of secret keys to sign and a set of messages we want to sign, but we don't want to create a link, and the signatures are created by multiple different parties. So the important feature is that no verification of any subset must be valid. So only if you verify all of them, you get all of them. And then what we do is we replace the messages by proxies, and we sign some random values, and we make sure that the random values and the proxies are equal. And then if we hide all the proxies and random values and show in zero knowledge that they're equal, then we can verify that without being able to verify any partial subsets. So the building blocks are all standard assumptions. It is quite versatile, so the way we describe it is that you can use whatever signature scheme you want, and we formalized it for a generic signature of knowledge for some NP language. And for one example is that you can do a standard Schnorr style signature of knowledge, which is like knowledge of a secret key to a public key. If you want anonymity, you can do a ring signature, so you know one secret key in a set of public keys, or you can do even a linkable ring signature, which is the thing we do. So why is it all secure? So the soundness comes from the simulator and the extractor of the signatures of knowledge, and then it reduces to the binding property of the commitments. The simulatability holds because the witness is only used in the signature of knowledge for the actual signing. So our wrapper does not have any secret input. And the privacy holds because the union of two fields, of two sets, is indistinguishable on how the set was created, and the addition in the field is also perfectly hiding. So thereby the mapping between inputs and outputs is hidden. So far, we showed that how to build these aggregatable signatures such that the inputs are only spendable if all messages of the required subset are in the final transaction message set, and that works even indistinguishable from full transactions. So you can only also create these as a single participant, and then they are not differentiable if they were aggregated or created directly. There are more features we need to achieve the full SwapCT system, and we described them in our paper, which is sender anonymity, which is achieved through a ring, so the signature is an actual linkable ring signature. Then we need receiver anonymity, which is achieved through one-time addresses, and value and type confidentiality, which is done through commitments and a zero-knowledge proof that the commitments are balanced. So to show that it's actually applicable, we implemented it in a not not only the bulletproof timing measurement, but we try to get a full transaction system, so we can say here is a transaction, please verify, with these reference inputs. And there we achieved very comparable numbers to the Monero implementation, which is based on years of performance tweaks. So we already achieved quite a good performance for the setting we wanted. And we are super happy with that, and we plan to continue improving it. So far, so good. Thanks for your attention, and I'm very happy to take questions.